Hello, welcome to another module in this massive open online course. So we are looking at the properties of and analysis of LTI systems. Let us continue this discussion. So we want to look at further properties. We are looking at further properties and analysis of LTI systems. Let us specifically look at memoryless systems. Now remember, in a memoryless system we have yt, the output, equals txt is simply equal to alpha times x of t. That is, it depends only on, that is, some constant k times xt, which implies depends only on the current input at the current time instant, correct? Yes or no? So it depends only on the input at the current time instant. Depends only on the input at the current time instant, all right, does not depend on the input at the past or the future time instants, all right. So that is known as a memory less system does not have memory, and hence the corresponding impulse response of this system would therefore be yt equals, so that implies impulse response ht would be k times delta t, correct, because the output depends only on the current input. So the impulse response will simply be a constant times delta t, since yt is k times, since the output is k times any input, the impulse response is simply the constant. So this is the impulse response this is the impulse response for a memoryless system. So it basically says that h of t equals 0 if t is not equal to 0. So it's non-zero only for t equal to 0, otherwise h of z is equal to 0 for t equal to t not equal to 0, or in other words, if, another way of saying this is, if h of t is not 0 for t not equal to 0, then system is not memoryless, then system will have system is not. If h of t is non-zero for t not equal to 0, then the system is not, h of t is non-zero for t not equal to 0, the system is not a memoryless system. Okay. So that is a characterization of the memoryless systems in terms, characterization of a memoryless system in terms of its impulse response. Okay. Now causality, another important property of LTI systems, if you remember, is causality or a causal system. okay, causality or a causal system. Okay. So, for a causal system, now remember, for any LTI system, as we have seen in the previous module, we have output y of t equals input x of t minus tau times h of tau d tau. Okay, this is the output expressed in terms of the input x of t, all right, and where h of t or h of tau is the impulse response of the LTI system. Okay. Now, this y of t for a causal system should depend only on x of t and past values of x of t. Okay. So, it should not depend on the future values of x of t, that is, so y of t for a causal system y of t should depend only on x of t minus tau for tau greater than or equal to 0, that is only past values of x of t. And this implies, so this implies now h of tau must be non-zero only for tau greater than or equal to 0, because if h of tau, you can see from this integral over here, if h of tau is non-zero for tau less than 0, then this will also pick up negative values of tau, that is x of t, that is x of t minus tau, where tau is negative, will depend on basically is a future value of the signal x of t. So, therefore, we need h of tau to be non-zero. So, h of tau not equal to 0 only for tau greater than or equal to 0, that is an important. So, h of tau must be non-zero only for tau greater than or equal to 0. So, h of tau, which implies and also implies h of tau equal to 0 for tau less than 0. So, this is basically denotes a causal, that is impulse response, okay, property of a causal. This is the property of a causal LTI system, that is impulse response h of tau equal to 0 for tau less than 0. And as a result, this integral can be simplified simply as y of t equals minus infinity to infinity x of t minus tau h of tau d tau. This integral can be simply simplified as from 0 to infinity, since h of tau, this arises since h of tau is 0, since h of tau equal to 0 for tau less than 0. Okay. So, that is the property of a impulse response. This is the property of the impulse response of a causal LTI system or a causal linear time invariant system. Okay. So, now, and therefore, the system is, now let us look at another property, non-causality. Non-causality system is non-causal if h of tau not equal to 0 for tau less than 0 or for some tau less than 0, and h of tau, the system is anti-causal if h of tau equal to 0 for tau greater than h of tau equal to 0 for tau greater than 0, and in this case anti-causal system, something interesting happens. Y of t depends only on future values of x of t, depends only on, you can clearly see if h of tau is 0, if h of tau is 0 for tau greater than 0, it happens that y of t depends only on future values of x of t. Such a system is known as an anti-causal system, right? H of tau equal to 0 for tau, or h of t equal to 0 for t greater than 0, or h of tau equal to 0 for h of tau equal to 0 for tau greater than 0, or h of t equal to 0 for t greater than 0. Alright, such a system is known as an anti-causal system. Okay, so we have causal systems, non-causal systems, and anti-causal systems. Okay, let us now look at another important aspect, that is the stability. In particular, let us look at Bibo stability, which we already described previously, that is bounded input, bounded output. This is an important, one of the most important criterion, important for or important criterion important form or important criterion for stability, and this is characterized as follows, that is Bibo implies, or we say system Bibo stable if input is bounded, magnitude of x t less than or equal to c, some finite value where c is some finite value, that is if magnitude of x t is less than or equal to c, then this implies that the system output, and this is for all t, system output must be less than or equal to some other constant k also for all t. That is if the input, that is basically implies magnitude of y of t, output is less than or equal to k. So, this basically implies that for any bounded input, that is when the input is bounded, correspondingly the output is also, that is any bounded input produces a bounded output. Okay, that any bounded input to the system must definitely produce an output that is upper bounded from by certain constant value. The system, if the system satisfies this property for all bounded input signals, this is known as a Bibo stable system. That is, it's a stable system under the Bibo criteria, that is bounded input, bounded output, stability criteria. Okay. Now, we will derive an important condition on the impulse response of the system, that is Bibo stable, and that can be derived as follows. If the system is B, we will show that system is Bibo stable, that is bounded input, bounded output stable if the impulse response is absolutely integrable, which is magnitude integral minus infinity to infinity magnitude h of t dt is less than infinity. That is to say, this quantity does not blow up, or this quantity is rather finite. Okay, that is this impulse response, another way of saying this is impulse response is absolutely integrable. Impulse response is absolutely integrable. Okay, and let us justify this condition. Now let us assume that assume we have a bounded input. Magnitude x t less than or equal to c, and let us say also assume magnitude minus infinity to infinity magnitude h t equals integral of magnitude h t dt equals some constant, let us say alpha. Then what we have equals the output. Now we have to show that the output is bounded. Now recall that the output is given for any arbitrary input signal x t in terms of the impulse response as well x t minus tau h of d tau. Therefore, magnitude y of t, if you look at that, the magnitude y of t, that is equal to the magnitude of the integral x of t minus tau h of tau. Now, the magnitude of an integral is less than or equal to the integral of the magnitude of the quantity being integrated. So, this is less than or equal to magnitude h of tau x t minus tau magnitude h tau d tau, but magnitude x t minus tau, this is less than or equal to c, because we assume that this follows from bounded input property. Okay. This follows from the bounded input property, which implies this integral is indeed less than or equal to c times minus infinity to infinity magnitude h t dt. This we said is alpha, so this is equal to c times alpha, which implies, so this implies basically that magnitude y t is less than or equal to c times alpha, which basically implies that the in output y of t is bounded. So, for what we have been able to demonstrate is that if integral minus infinity to infinity magnitude h tau d tau is a finite quantity, then every bounded input will produce a bounded output for the LTI system. So, this output magnitude y t, so this is a bounded output, and this is your constant k that we are talking about initially, magnitude y t less than or equal to k. So, any bounded input produces a bounded output. So, the condition for Bibo stability is as we have derived, this is the condition for LTI system to be, this is the condition for condition for LTI system to be Bibo stable. This is the condition for the Bibo condition for bounded input bounded output stability of an LTI system. Now, another important aspect that we can take a look at is that of the eigenfunctions of an LTI system. Eigenfunctions of an LTI system. What are the eigenfunctions? So, another aspect that we would like to take a look at are eigenfunctions of LTI systems. And for an eigenfunction of LTI system, consider, to illustrate this property, consider xt equals e to the power of alpha t, where alpha is some constant. Now, for an LTI system, we know output y of t equals, in terms of the impulse response for any arbitrary input signal, x of t is given as x of t minus tau h of tau d tau. Now, I am going to substitute the expression e power alpha t for x of t. So, this gives e power alpha t minus tau h of tau d tau, which you can now simplify it as, remember, look at this, e power alpha t is a constant that does not depend on the integration variable tau. So, that will come outside. So, this is e power alpha t integral minus infinity to infinity h of tau e power minus alpha tau d tau. Now, if you denote this integral by h, capital H of alpha, you can simply, so it depends only on the impulse response h of t and the constant alpha. So, this is h of alpha times e of alpha t. So, what you are able to show is that t of e power alpha t, when the input is e power alpha t, this is simply a scaled version, that is output, that is, if you look at this output to e power alpha t equals some scaling factor times again input signal, the same input signal multiplied by s. So, we have y of t equals some constant, that is output signal t, output signal t of x of t is some constant k times x of t, correct. So, it is the output is simply a scaled version of the input, that is a better way to say this. Output is a scaled version of the input. Okay. So, better way to say it is output is a scaled version of the input. Remember, in matrices, wherever you have a matrix A and vector x bar such that A x bar equals lambda x bar, remember, if you remember from your basic knowledge of linear algebra or properties of matrices, whenever we have a matrix A, alright, and a vector x bar which satisfies the property A x bar equals lambda times x bar, that is, if you treat this as a linear system, in fact, this is nothing but a representation of a transformation or a linear system. So, this is a matrix, okay, this is a matrix, this is a vector, okay, and a vector satisfying this property is termed as the eigenvector, okay, which means that A times x bar, which is basically input to the system, input to the transformation characterized by A, is simply lambda times x bar, scaled version of x bar. So, this x bar is called an eigenvector and lambda is called an eigenvalue. Okay, lambda is called an eigenvalue. Similarly, what you are observing here is that the input is E alpha t, output is simply a scaled version of E alpha t, that is h of alpha times E alpha t. Therefore, this is known as E of alpha t. Hence, E of alpha t is equals the eigenfunction of any LTI system. And these eigenfunctions play a very important role, because if you look at this h of alpha, okay, this is equal to minus infinity to infinity h of tau e power minus alpha tau d tau, this is known as a transform. Okay, this is known as a transform of the impulse response h of tau, and there can be several such transforms depending on the nature of alpha that is chosen. It can be the Laplace transform or the Fourier transform. It can also be in the continuous time and discrete time, something the discrete time case we will talk about that later. So, there can be various transforms, and these transforms and eigenfunctions are very fundamental to the analysis and to understanding the properties of LTI systems. Therefore, this property is extremely important. So, transforms, which we will look at subsequently at later stages in this course, transforms play a very important role in understanding and in analysis. Let us put it this way, in analysis therefore, eigenvalues are very key, eigenvalues are of significant importance. Okay, or let us put it this way, eigenfunctions, I am sorry. The transform is nothing but the eigenvalue. In fact, you can see now from the context A x bar equals lambda times x bar, this is nothing but this is equivalent to the eigenvalue under this particular transformation, is nothing but the eigenvalue corresponding to this eigenfunction. So, eigenfunctions are very important for the understanding of eigenvalues are very important for the understanding of eigenfunctions are very important for the understanding of LTI systems. Alright. So, in this module we have continued our discussion on the properties and analysis of LTI systems. So, we have looked at several properties. Let us stop here and we will continue this discussion in the subsequent modules. Thank you very much.